All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is heating curve worksheet number 1, the first of 2 installments on heating curves. So let's start by deciphering exactly what this curve means. Well, we're going to look at the x-axis first. We have time in minutes on the x-axis, and then we'll look at the y-axis, temperature in degrees Celsius. Now what's happening is we're going to take a substance, we'll call it substance X, and we're going to apply a constant amount of heat throughout this process. So starting with time 0 and going on into the process, we're going to apply a certain amount of heat in kilojoules to this substance X. Now we'll start at time 0 at this temperature here, 30 degrees Celsius. As we apply heat rather, I should say, we're going to see that the solid, because that's what the phase is in this part of the graph, the solid is beginning to warm, right? But throughout the process, from here to here, from this part of the curve to this part of the curve, we're going to have a solid. Now, at this point of the curve, something's going to happen, and that is that the solid is going to begin to liquefy. All right, the solid is going to begin to become a liquid through this process in Roman numeral 2. Now, it's interesting to note that the temperature does not increase throughout this process in number 2, Roman numeral 2. It does not begin to increase until every last remnant of the solid has melted. All right, every last bit is gone. And so then what's going to happen is the liquid, it's entirely liquid now, is going to be getting progressively warmer and warmer and warmer until we get to this place here. And then what's going to happen is that we're going to convert the liquid into vapor or gas. But notice again, throughout this process, there is a constant temperature. The temperature does not increase, even though we're applying a consistent amount of heat, until all of the liquid has vaporized. At that point, then of course, the vapor will be, or the gas will begin to heat up, right? So that's the process we're dealing with now, all right? Heating a substance. So let's answer some questions. First question is this: in what part of the curve would substance X have a definite shape and a definite volume? Well, clearly, we're talking here about a solid, right? So where is the solid? Well, if we look on the graph, we can see that the solid is this part of the curve. So everything in this initial part of the curve is a solid. That would be Roman numeral 1. So we'll answer Roman number 1 with a Roman numeral 1. That's our answer right there. Number 2, in what part of the curve would substance X have a definite volume but no definite shape? Well, that would be, of course, a liquid. So where does that happen? Well, if we look at the curve, that's Roman numeral 3, right? By this point right here, we've already converted all of the solid into liquid, and now in Roman numeral 3, the liquid is becoming warmer, right? So Roman numeral 3 is where the liquid resides. So we're going to put Roman numeral 3 for number 2. Look at number 3. It says, in what part of the curve would substance X have no definite shape or volume? Well, we're talking about a gas here, and that's going to happen here in Roman numeral 5. Once we get to this point right here, all of the liquid has been vaporized, and we're heating a gas here. So the gas resides at Roman numeral 5, just like that. So we'll put Roman numeral 5 for number 3. Let's look at number 4. In what part of the curve, or what part of the curve represents a mixed solid liquid phase of substance X? So let's go back up now, and the solid liquid phase is going to reside right here. In other words, at Roman numeral 2, we're going to have a mixture of solid and liquid, right? Now, at this point here, it's entirely solid. At this point here, it's entirely liquid. But as we move or progress from here to here, the amount of solid is decreasing, the amount of liquid increasing, right? Amount of solid decreasing, amount of liquid increasing until the ratio is on this point right here, all liquid, no solid, right? Over here, all solid, no liquid. Over here, it's some percentage of solid that's decreasing, some percentage of liquid that's increasing, okay? So that would be Roman numeral 2. So at Roman numeral 2, we have a mixture of solid and liquid. Now let's go on to the next one, number 5. Number 5 says this. What part of the curve represents a mixed liquid vapor phase of substance X? So it's going to happen right here. So right at from this point here to this point here, from here to here, we're going to have a liquid vapor phase. In other words, as I continue to heat, the liquid is going to vaporize. As I go from left to right, I'm applying constant, steady energy. And at this point right here, we're going to have the mixed the substance is going to be entirely in the gaseous form, right? So it would be Roman numeral 4 for that answer. So we'll write that. Liquid vapor form, Roman numeral 4. Okay? Let me write that just a little better. So what we're going to be doing is we're going to be, again, moving across left to right, increasing the heat, and thus increasing the energy associated with these things, right? With this substance X. They asked me, what's the melting temperature of substance X? Well, where does melting happen? On the curve, melting is going to happen right here. From here to here, melting happens. What was that temperature? Well, I'm going to estimate, if this is 30 and this is 60, that would be 45 in the middle, approximately. And so let's just see. I'm going to approximate that to be about maybe 52, something like that. You may go a little higher, a little lower. I'm just going to say 52 degrees Celsius for number 6. So 52 degrees Celsius for that one. And let's go to number 7. What is the boiling temperature of substance X? So the boiling temperature, remember, is the intersection between liquid and gas. When liquid boils, we call that when liquid becomes vapor or gas, we call that boiling. So that's pretty easy. We just go straight across, and that's going to be 90 degrees Celsius, right? So 90 degrees Celsius is where the liquid becomes vapor. So we'll put that in right there. In what part of the curve would increasing kinetic energy be displayed? Well, anywhere you have solid being heated, liquid being heated, and gas being heated, and the curve is in upward diagonal, you're going to have an increased kinetic energy, right? So in this part of the curve, for example, as you heat the solid, the particles themselves will begin to move more rapidly, bang into each other a little bit more frequently, and until you get to the liquid phase. Here in Roman numeral 3, the same thing. This time, on average, they're more energetic. They're moving around a lot more, but they become even more energetic if you move from left to right. And the gas, of course, is the same thing. So that would be Roman numeral 1, 3, and 5. We are increasing the kinetic energy. So we'll put that in. So 1, 3, and 5, we're increasing kinetic energy. In what part of the curve would increasing potential energy be displayed? Well, if throughout the curve, if at all times we're putting energy into the system, and we know kinetic energy is causing the increase in temperature here, here, and here, but we know at 2 and 4 we're also putting energy into the system, but the temperature isn't rising. So if the temperature is not rising, that means the kinetic energy isn't increasing. But we know we're putting energy in. So where's it going? Well, it has to be going into potential energy. So Roman numeral 2 and 4 would be the places where potential energy is increasing. So we'll write 2 and 4 for number 9. Number 10, in what part of the curve would the molecules of substance X be furthest apart? Well, gases have their particles furthest apart in general. So that would be Roman numeral 5 is where the molecules themselves would be furthest apart. That's where the gases are. So we'll put Roman numeral 5 for number 10. And in what part of the curve would the molecules of X have the lowest kinetic energy? Well, their lowest kinetic energy on average is going to happen when it's a solid, and that happens here at Roman numeral 1. So for that one, we're going to write Roman numeral 1, just like that. And number 12, in what part of the curve would the molecules of X have the greatest kinetic energy? That's going to happen in the gaseous phase. So we'll look for the gas. It's Roman numeral 5, and we'll put Roman numeral 5 for number 12. And we are done with this particular worksheet. I tell you what, let's go ahead and take a look at one thing before we finish up, and that is this. I want to talk a little bit about calculations and how to calculate things on this graph before we go to worksheet number 2. Folks, if you want to know the amount of heat necessary to move from one place to another at Roman numerals 1, 3, and 5, you're going to use this formula. You're going to use heat is equal to the mass times the specific heat times the change in temperature, right? So if I want to move from, say, here to here, I'm going to multiply the mass of that solid times its specific heat. Now make sure you know the specific heat for that substance times its change in temperature. So going from here to here, whatever that change in temperature is what you're going to put in for the change in temperature there, right? So again, that's formula Q is equal to mc delta T is going to be used at 1, 3, and 5, right? Now, in order to calculate the amount of heat necessary to go from solid to liquid, we're going to use a slightly different formula. That heat is going to be equal to, and I'm going to use Q for heat, is equal to the number of moles, right? The number of moles of that substance, not grams, but moles, times the heat of fusion, what we call the heat of fusion. It's a number that you have to look up in a table, or someone has to give it to you. And when you multiply those two numbers, it's going to give you the amount of heat, usually in kilojoules, right? So in kilojoules, generally, to determine the amount of heat to go from solid to liquid. Now, if you want to go from liquid to gas, you're going to use almost the identical formula. We're going to say Q is equal to the number of moles that you're dealing with, right? Times, this time we're going to use the heat of, I'll abbreviate this with a V, heat of vaporization. Again, you're going to have to look that up in order to determine the total, in order to determine the amount of heat necessary to go from liquid to gas. So you'll often be asked, for example, to say start down here with a liquid and begin here with a gas, or start with a solid and begin with and end with a gas, and you need to know how many joules or kilojoules of heat are necessary to do that. So to do that, what you're going to do is you're going to use this formula mc delta T to go from the cold solid to its melting temperature, right? And then you're going to use this formula to go from to melt the substance, and then you're going to use this formula again, Q equal mc delta T, to heat up the liquid, and then you're going to use this formula to determine the amount of heat necessary to vaporize the liquid. And then what you're going to do is you're going to go back to Q equal mc delta T to determine the amount of heat necessary to go from the liquid gas interface to the blue dot that I've shown here, the heated gas. And that'll do it for this worksheet. I'll see you in the next one. Thanks. Bye-bye.